So in our last video, we should have noticed that the product of a binomial with itself and the subtract in between, we just end up with the square of the first term. We're going to have take away twice the product, or it's still twice the product, and then square the last again. So it's still a perfect square trinomial. Anything you can write it as an exponent, as a base with an exponent of 2, it's called a perfect square. So this is a perfect square. What if we multiply two binomials that have the same terms, but this time they don't have the exact same sign? So it's not the square of our binomial that we're figuring it out. They have opposite signs. So this one has a plus and this one has a minus. These are called conjugates of each other. These binomials are conjugates. I spelled that wrong. Conjugates of each other. So they look exactly the same, except one has a minus and one has a plus. If we hop that x through the first bracket, from the first bracket through the second bracket, we're going to get an x squared and a minus 4x. And then if we multiply the plus 4x through that second bracket, we're going to get a plus 4x and a minus 16. Now when we collect those like terms, we're going to end up with x squared, but the middle terms end up canceling each other out this time. Instead of being the same sign and ending up doubling, they cancel out, and we're just left with two terms in our answer. So this one gives us can't speak today. This one gives us an x squared minus 16. All right, so try the next two, multiply them through, and see what you get as your answers. Okay, you should get a 4x squared on this one. 2x times 2x is 4x squared. A plus 1 times the 2x, or the 2x times the plus 1, is a plus 2x. And now it's minus 1's turn. We're going to get a minus 2x. That cancels out with the plus 2x, and then a minus 1. Minus 1. That gives us 4x squared minus 1 as our answer. So there's only two terms in our answer this time. We're going to get a 25x squared, a minus 15xy, and then we get a plus 15xy, and then a minus 9y squared, leaves us with an answer of 25x squared minus 9y squared. So you'll notice in these examples, when we have the conjugates, the two middle terms end up canceling each other out and disappearing completely. So we just end up with a perfect square minus a perfect square. So our pattern is really, this first term is the square of, or the product of the first two, or the first in the both brackets, and then we end up with the product of the lasts in the brackets. So the middle part disappears. All right, so we end up with a squared minus a b squared. We don't have that double the product this time. So why do we care? So these patterns that we have for this particular lesson are important because when we want to work backwards to be able to take the standard form or the expanded form and rewrite it in its factored form, these patterns will help us get there. So this is going to be our focus for the next lessons after this one. Can we work backwards? Try to rewrite each of the following expanded polynomials using one of these three patterns, either the square of the binomial with a sum in between, or the square of a binomial with a subtract in between, or the conjugates of two binomials. All right, so I'm noticing I have a perfect square here and a perfect square here. Here I have a minus 12x. So maybe this is the one, if I work backwards, I'm going to square root this. I'm going to square root that and get 2x. And I'm going to square root the 9, and I'm going to get a 3. And because I have a subtract here, I'm going to put a minus here. And that should all be to the exponent of 2 if I've done this correctly. So I could check that if I were to be nice and write that out twice. 2x minus 3 times 2x minus 3. I'm just checking my work here. I'm going to get a 4x squared. Oh, that's good because that's what I had. I'm going to get a minus 6x, and then a minus 6x again, and then a plus 9, which combined together I will get that. So I know that this is the correct working backwards form right here. This is my working backwards, or what I call the factored form. Similarly, this is a perfect square here. I could take the square root of that and get 10x. This is a perfect square here. I could square root that and get 7. I'm going to take the sign from the middle and write that to the exponent of 2. And if I check that by being nice writing that out twice, I am going to get 100x squared. If I take the product of these two, I get my 70x, and when I double it, I get the 140x, and square the last, I get the 49. So I know I've done that right. And the last one here, square root the first, square root the last, sign from the middle, all to the exponent of 2. If I were to be nice, write that out twice, expand and simplify, I would get my x squared. I'll get my plus 3x doubled would be plus 6x, and square the last. This one only has the 2 terms, and they are perfect squares. That means they're going to be conjugates of each other when I factor it. Square root the first, that's going to go at the beginnings of my brackets. Square root the last, that goes at the ends of my brackets. And then I just have to have opposite signs in between to make sure that middle term disappears. So now you've learned some quick little ways of what we call factoring. And it's important to be able to write our quadratics from standard form into their factored form, because they help us get our x-intercepts. That's the whole point of being able to write it in its factored form. The x-intercepts help us to graph. It also helps us to get those max or min values.